Thank you very much. Thank you very much for arranging this and giving me the opportunity to talk about flash technology basics in the light of what we and you as SSD users should know about the very basics of the flash memory technology, which has an impact to the operation and the constraints of SSDs. So, I mean, what is the issue with the SSDs? The issue with the SSDs is that we can only write an finite amount of data into an SSD. And that makes the usage of SSD different from the hard disks. For the hard disk, we weren't used to any limitation of writable data. Yeah, you can write on the media on kind of a single sector or block as much as you want, kind of 24 hours over all the lifetime, writing, there will be no issue. So the IT community was not used to care about the right workloads. However, for the SSDs, there are differences. So we have client SSDs which can write 0.1 to 0.3 times the capacity every day over its lifetime, and assume this is a 500 gig SSD. So over 3 years, every day, let's say 0.3%, 0.3 times, that adds up to 160 terabyte of total amount of writable data into that one. That's pretty okay for a laptop. Yeah? Like 500 gig, 0.3 times is 150 gig a day. No one really creates 150 gig a day by his hands. However, in server and IT applications, there are applications that create that amount of data to be stored into storage devices. And at the high-end model of SSDs with 30 disk writes per day, so 30 times the 500 gig capacity, it's 50 terabyte a day, or it adds up to that one would, over its 5 years lifetime, can absorb, you can store about 27 petabyte. So 160 terabyte, 27 petabyte here. So that's a major difference, although both are 500 gig SSDs. That one would cost, the 500 gig version would cost about $200, and that one would cost about $2,500. So there is a fundamental difference, and this, well, to understand this, to understand the importance of the right workload, the assessment of the right workload, I want to explain why this comes. Kind of what's the difference? First of all, why it is limited, what the manufacturer like us are doing to kind of mediate it out, make it still usable as a kind of ordinary storage device, and what are the difference between this technology and that technology. All this is more like hello? Okay. All this is more like a lecture. It's not a product presentation. It's also not Toshiba specific. All what I'm telling is it's general technology. It's just that the product photos are from Toshiba because I have the most easy access to them. So diving very deep into the flash memory technology. So in an SSD, we are using as the memory component, as a storage component, the NAND flash. It's a kind of semiconductor storage, and this is a very simplified cross-section of the single NAND flash memory cell. I'm explaining it simplified in a way targeted to the understanding we need to develop. A semiconductor technologist would tell that it is kind of too simplified or maybe wrong. But just keep in mind, we need to develop a model for us to understand. So, back to the memory cell. So the major part of this memory cell is what we call the floating gate. The floating gate is a small piece of silicon where we can store electrons, where we can store a charge. This charge is kind of very well isolated with an isolation layer around the floating gate. We can bring the charge by charging the control gate and letting the electrons tunnel into the floating gate. That would be the writing process of the flash cell. And then we can apply a voltage in this transistor, and if there is a charge a current will flow. If there's no charge, no current will flow. That is the reading process. So that's kind of easy. There are no problems with that operations of kind of charging to this floating gate and reading here. However, our optimization criteria for this flash cell is we need this floating gate as good isolated as we can do, because we want to keep the charge. This is a non-volatile memory. We want to keep the charge as long as possible, and charges tend to leak out if it's not well isolated. It's not well trapped in isolation layers around. So we are isolating this as best as we can. And this gives a contradiction to the erase process. So in case we want to erase this against the very well isolated layers around, what we have to do is we need to apply a very high voltage here in order to squeeze the electrons out of this floating gate to uncharge it. And the voltage we have to apply here is about 10 volt. The isolation layers is less than a nanometer nowadays. And the electrical field is measured in volt per meter. So 10 volt over a few nanometer is a very high electrical field. And this high electrical field is comparable to the flash of a thunderstorm. So in the amount of electrical field on this small area is like the electrical field in the flash of a thunderstorm. This is, by the way, why it's called NAND flash. So the erasing process of the flash cells reminded the guys which invented the NAND flash, Toshiba guys, in the early 80s, reminded them to the flash of a thunderstorm or the digital camera, or the digital camera we didn't have at that time. But anyway, so we set an electrical field like the lightning flash of a thunderstorm, and actually this flashing or erasing process with the 10 volt here is giving the structure causing the same damage, similar damage like the lightning flash of a thunderstorm. So this electrical field is so high that it causes cracks in the isolation layer, it causes impurities in the isolation layer, and as a consequence of that, we are damaging the isolation layer, and the charge we put here in order to store a 1 or a 0 tend to leak out over time. On a fresh, well-isolated cell, the charge we are putting here will stay forever. We have in our labs cells of the early flash generations which were just written once and not erased at all, and the charge after 10, 12 years is still there. Yeah? However, if it is erased many times, there are more and more cracks, more and more damages to the isolation structure, the charge leaks out, and we set to ourselves a threshold of 3 months of retention time without any power. So if we make so many damages to this isolation layer around that it won't keep the charge for 3 months, we declare the cell as dead, written to that. So that's basically the end of the life of this flash cell. One other thing which we should remember when kind of going from that cell to the structure and finally to the SSDs is that the writing and reading can be done on a small granularity. Yeah, we can theoretically write with accessing the control gate each bit cell by itself individually. And an NAND flash is organized then in pages, but the pages are fairly small because there is no issue in controlling it into the small granularity. However, putting a 10 volt here, which is a very high voltage, we can only do this in larger granularities. We cannot do 10 volt just to one cell. So we can do the 10 volt to larger pages, which are then isolated. We cannot make the pages smaller because then we have an issue with the density. This is the symbol of the floating gate. So here, this symbolizes this floating, well-isolated gate. Before going to the flash structures, just a few words why we call it NAND flash, so that everyone is aware. everyone talking about NAND, sometimes even just NAND. And we call it NAND flash because in the flash memory devices that we are using for the SSDs, the floating gate transistors are arranged in a series and can be read out in a series of data. And this serial connection of floating gate cells reminds like the NMOS transistors in a NAND gate, so also connected in a series. Advantage of this structure is we can make it very dense because we can merge the readout transistors into each other. We don't need any tubs or any wires in between. So the NAND flash, by its construction, is the most dense memory technology. But due to the serial structure, it is not the fastest one, and is not the bits cannot be individually accessed. That's okay for storage. We are anyway asynchronous, and we are block, file, object whatsoever based, and not bit based. There is another technology based on the floating gate, which we call the NOR flash, where each transistor has his own wire. So they are arranged in parallel, like the NMOS transistors in a NOR gate. So this technology is called NOR flash. It has much lower density, but it weighs faster because of the individual access. And this NOR flash technology is used in code memories, like the ROM and a microcontroller nowadays is still using this NOR flash technology. Its density is, let's say, less than a tenth of the NAND flash technology. So back to NAND flash. Here we can see this series of floating gates again in the symbol, and in the ideal structure. So control gates, floating gates, the read transistor, and here the read transistors are merged like that into a series. This is how it looks in a kind of ideal picture. In reality, this is a picture from the current 19 nanometer generation. So here you can see again the control gate. This is the floating gate. It's isolated with kind of silicon dioxide kind of glass layers up and down, and with air gaps to the left and right. And the small thing here is the readout transistor. This structure is pretty small. If this is 90 nanometer, then
30 atoms.
Yeah. The human hair, which is 80 micrometer, would be in the same scale of the whole building. The diameter of a human hair would be the whole building. And this is also kind of why it looks a little bit strange and odd and different from cell to cell, because we are manufacturing it pretty small. It's already a miracle that it works like this. That it works at all. And we are going to 15 nanometer and 12 nanometer structures pretty soon, until the end of the decade latest. So what this picture also tells us is that the cells are different from each other. Sometimes the floating gate is larger, it's smaller. The isolation layers are different. Also the implants here in the transistor are different. So from cell to cell to cell, it behaves different. We should take this into account when we later go to the different technologies. So keep in mind, we would like to do it more accurate, but we are on a very small scale, and semiconductor tend kind of all implants, all electrical parameters, all physical parameters are, as in any manufacturing process, in a kind of Gaussian distribution around the center point. We would like to have this as small as possible, but on the other hand, it's a matter of economics, so we have to allow and budget for a certain Gaussian distribution. So, how we save data in these cells? We can save initially, when flash was brought to large volume production, let's say at the end of the 90s, we save 1 bit into one of these cells. Simply, if there was a charge, it was a 1. If there was no charge, it was a 0. So 1 bit per cell. The problem comes when we put a certain charge, let's say 100%, and then we erase. We erase, erase, erase. We damage our floating gate, our isolation of the floating gate, and the charge leaks out. It leaks out over time, and at a certain point in time, we may read out the wrong value because the charge has leaked out. And again, this is this 3 months threshold with power off. So we can only allow an amount of damages that makes the leak out process so fast that after 3 months, it's just here. If then more damages, after 3 months, it may read out the wrong value. This so-called single-level cell technology, stored just 1 bit per cell, brought us the USB sticks and SD cards in the megabyte range, and the very early SSDs where we had 32 gigabyte or 64 gigabyte for a lot of money. Because it's only 1 bit per cell, so we need a lot of silicon, and that's very expensive. So pretty soon, industry tried to put more than 1 bit per cell, and bringing, let's say, SSDs into ranges which they are commercially attractive against hard disks for certain applications, and also bringing the kind of double-digit gigabyte SD cards and USB sticks. We need to save more than 1 bit. And this is what we call the multi-level cell. Actually, the initial multi-level cell could be also a kind of dual-level cell because we are saving 2 bits. We are doing that in a way that at the same physical structure, we either put a full charge or no charge or 1/3 or 2/3 of charge, and we are coding it into 0, 1, 1, 0, and so on the same physical structure. These are not 2 cells. It's just the readout electronics is different. So we can write in kind of more granularity charge levels, and we can read more granularity charge levels. And if we have written, let's say, 66% of charge, and then the leak out process starts because of the damages, we are much quicker on the wrong value than for the single level cell. And this is why multi-level cell, even if it was on the same physical structure, is less robust and can tolerate less erase flash damages than the single level cell. Well, if there were just a few cells giving out the wrong value because of this leakage, we can still tolerate this because there's an error correction. Yeah, but more or less, if the writing process into a storage device is well distributed, many of them will fail if many have the same amount of damages. So then the error correction would not really work anymore. For terabyte SSDs, we need to put even more bits into one cell. And this is what we call the triple level cell. So here we are coding no charge, full charge, 7/8, 6/8, 5/8, and so on, to code this into 3 bits. And here it is obvious that we cannot allow much of erase damage, because then we are immediately into the threshold to the wrong value is fairly small. This is why a triple level cell for client application still work, because we do not have to erase too much. For enterprise application, it needs a kind of very well managed error correction and a lot of over provisioning, meaning spare cells to kind of mask out the cells that are so leaky that they go to the wrong value. There are 2 technologies in between which I would like to mention as well, which is, industry called it enterprise MLC. Enterprise MLC is a normal MLC technology, just we are screening out the devices that on the wafer or on the chips that are falling into the center part of the Gaussian distribution of all this parameter that we have seen earlier. Actually, in the Gaussian distribution, a lot of parts are in the center. We cannot just throw away everything which is outside of the center. This still works for client applications, but the ones are in the center, we can screen them with smart screening methods. And what it effectively brings is the devices where if we want to write with 66%, we write not here and not there, because if we write there, we can tolerate less damages for the wrong value, but we are using only that once where if we write 66, we are exactly at 66. And this gives us higher margin, more erase cycles tolerating until we are leaking out to the wrong value. So it's just a selection process that selects somehow the good devices where we are sure we are writing into the center. The yield of this selection obviously fluctuates, but with good quality control, with a good process control, there are in many times kind of more than half, if not 80%, are enterprise MLC quality. It can be used at enterprise MLC quality. One other technology is called pseudo SLC, and this is just using the normal MLC technology and writing just one bit. It's kind of somehow going back to this technology, but kind of on the same physics of that one. And here, obviously, if we write a full charge, we can tolerate many erase damages until we are at the wrong level. So this gives a very robust structure.
You talked about the sort of 3-month time, power off time. Does this mean that if you keep it powered on, the controller's actually continually going through and perhaps refreshing cells that are leaking so that they'd last longer than 3 months if it's powered on?
Yes. If you, in an SSD, the data content is constantly shuffled around. We will see this later. So that if you keep an SSD on power, it shuffles around the data in less than 3 months, so that you won't have an issue. Yeah, it's just that it's a matter of definition. Our definition, our data book says that you unplug it, you put it in the cabinet, and it should have the data still after 3 months. Well, it also means that if you reach the 3 months endurance point and you leave it powered, you could still use it. But we cannot give any warranty or any prediction about kind of when it will reach a state where, for example, a unforeseen power cycle. So server goes down in the evening because of a power breakdown. Your power supply does not come back until the next morning. We don't know whether the data is still there. We don't know when exactly this point is. We can only say this 3 months is point in time. Okay, so all what I said before, from what does it mean for the flash components? So we can say that for an SLC, there are 100,000 or more erase cycles possible until it reaches this 3 months retention point. MLC, it's about 5 to 10,000 erase cycles. With the screening the center devices out of MLC, we can push this to 30,000 cycles. For TLC, it's only about 1,000 cycles. And it's important to understand, in a hard disk, there is no physical limit on the media. You can flip the bits in the magnetic media, that there's no physical limitation. It's just that if you calculate the workload, the normal workload that a hard disk consumes over 5 years, then we can say if this all goes to one single block, it's about 10 billion or more. What is also important is that this is not really a reliability issue. Yeah, after 10,000 erase cycles, the cell is dead. It can't keep the value for 3 months, and it's not some after 2,000 and some after 8,000 and some after 50,000. We don't need kind of reliability tests to predict this. We can write in our flash components in the testing to determine these values quite fast, within a few hours. So we can easily measure how many write cycles they will accept. And if there are over the amount of write cycles, they are just dead. For an SSD means if you have used the amount of data you can write into an SSD, or you can actually erase into an SSD in order to write new, the SSD is dead. You consume the resource of the SSD. It's like the gas in the tank. Yeah? If you have consumed the resource that you have bought, the SSD stops. If you have consumed the gas in your tank, the car stops. And it will definitely stop. It does not stop with a certain probability. If it's empty, it just stops. And also, it is not a reliability issue in a way that you can go back to your car dealer and say, well, my car stopped. Do something, return it, give me a new one. SSD is exactly the concept. If you've written it to death, you have consumed the resource. And this is something we in IT has to understand, and this is different from the spinning disks. So we simply have to watch our gas consumption of our system in order to make sure we manage that. And as this was not known with the hard disks, it's somehow kind of difficult to develop a common understanding. Also, I have to admit that kind of the SSD manufacturers did not always explain it too much in detail in order to kind of make everyone aware about this issue. Okay, here's just written the writing goes in pages of 4 kilobyte. So with a small granularity, the erasing goes in, depending on the structure, 128, 256, or 512 kilobyte big blocks. And if we want to erase just a 4 kilobyte page or rewrite a 4 kilobyte page, it may happen that we have to erase a full block. So with a read, modify, write cycle. So this is why these erase cycles of the single level does not really map to the full capacity of the SSD, because we have what we call the so-called write amplification. So if we write many small blocks which are scattered in the many small pages which are scattered in the larger blocks, we may have to erase a lot of unnecessary data which consumes the valuable resource. So what do we do to not to bother the user with the write endurance or erase endurance issue of the single flash cell? So first of all, we need to do aware leveling. In a hard disk, there's a lot of activity in a very few sectors. If we would do this in an SSD or in any storage component, SD card or USB stick, and if you always write or erase one area, it will be erased to death pretty soon. So there is the aware leveling, and the aware leveling is based on the block erase counting. So for any of the physical blocks into an SSD, we have an erase counter. This erase counter counts the erase cycles, and the easiest or the kind of most simple wear leveling is called dynamic wear leveling. Dynamic wear leveling means whenever a new data comes, we look for the block which has the lowest erase counter and write it there in order to treat or damage all the cells in the same way. Static blocks which are there but never overwritten just remain where they are. This is, for example, done in USB sticks and SD cards. For SSDs, the issue of the static block remaining may become an issue. So imagine this scenario: you have a 128 gig boot disk where there's operating system, where there is application software. If it is a laptop, there are the family pictures and some data sheets that are never changed. And you do your active data, your hot data, your lot of erase cycles on the upper 28 gigabyte. Then the first 100 gigabyte remain at erase counter 0 because they were just one time installed and sit there. And you are increasing the erase counter of the upper 28 gigabyte quite fast, and you wouldn't have much fun with your SSD. So in an SSD, we implemented what we call the static wear leveling, which means that also the static blocks, even they never overwritten or never erased, are erased by the controller of the SSD. It kind of is just shifted to a different area in order to, let's say, from time to time. So shifted to the upper 28 gigabyte if they have a rather high erase counter in order to level this out over the whole area of the SSD. Here, I mean, I said USB stick. For the USB sticks, we don't need the static well leveling because the use case of the USB stick or the SD card is different. We don't have operating systems. We don't have any hot data there. We just store the data and leave it there, and they are not overwritten so often. What is also done is the capacity over provisioning. So more cells than actually available for the user. Even if an SSD has, let's say, 1,000, even if an SSD has installed a terabyte of flash, that's actually in 2's complement. So 1 gigabyte of flash is 2 by the power of 30 bits, which is 1,730,000,000 bytes. While what we are providing to the user accessible data is 10 by the power of 9, so which is 1 billion bytes. So there's already a 7.4% over provisioning just by the internal structure of the flash, the 1024 by 1024 versus the 1000 by 1000 by 1000 for the external capacity. So 7.4% of over provisioning you will find in any SSD. And for enterprise SSDs, we are going to higher levels. So if there was 256 gigabyte flash installed and we give only 240, this gives a level of 12% over provisioning. And if we have 256 gigabyte flash installed and on the label we provide only 200 gigabyte, this is this 37% over provisioning. The over provisioning also is important for the consistent write speed of the SSD. I said earlier, to erase, we need to charge the 10 volt, and we need, first of all, to generate the 10 volt, and we need to apply the 10 volt for some time in order to squeeze out all the charge there. And this takes time. So the erase cycle of an SSD takes very long time. And if a full stream of data coming into an SSD and there is no free cells and the SSD has to start erasing cells, then the SSD drops in performance quite drastically. The only way to do something against this is to have spare areas available where there can't be any user data so that the SSD can do some offline pre-erasing and then accepting the SSD. And if this kind of the area that the SSD can manage by itself in order to have it pre-erased and available for new data is just 7.4%, and if this is full and the SSD cannot erase quickly enough, then the performance drops. And we see performance drops in SATA SSDs from kind of several hundred megabyte of the data sheet when they come fresh out of the box to double-digit or even single-digit megabyte per second. Yeah, if we run into this trap. With higher over-provisioning, there is more room for pre-erasing. Well, other things in the endurance management is the bad block management. So the SSD checks the parameters of the writings, and if there's something wrong, if the SSD detects that there's something wrong in the flash, different blocks are assigned. And the process of the garbage collection, meaning that if there are not used pages in blocks, the SSD consolidates the pages into one single block and erases all the other blocks where the data was consolidated off into one single one in order to have more free data available for kind of fast write data coming. Well, the SSD need to know which data can be erased and this is the more kind of philosophical discussion about this trimming stuff. And operating systems are still designed for hard disk. For hard disk, we can just overwrite. There's no such process of erasing. So files are labeled as I don't need them anymore, and next time they can be overwritten. In an SSD, the SSD like to know in order to trigger this kind of pre-erase operation. If it comes from the operating system, it's okay, but in server and RAID applications, this doesn't really work. Well,
I'm going to have some questions about that after.
In reality, kind of in theory, we can do a lot of things. In reality, from what I see in the field, it never really works. And if you want a consistent write speed, you should rather select SSDs with higher over provisioning. Yeah, not to rely on the trim. It depends from supplier to supplier, from manufacturer to manufacturer. It is this from model to model. It is not really standardized. So this write endurance, or actually erase endurance, is the key criteria for the SSD selection, for the SSD price per gigabyte, and also for the endurance class of the SSD. Actually, the real criteria is the total amount of writable data, so the gas you have in the tank. But this is depending on the capacity. Yeah, a double capacity has double the amount of total writable data, even if it is the same endurance class. So it's a little bit difficult to compare and difficult to handle, and especially for purchasing guys who need to know the classes, like the 10K RPM is more expensive per gig than a 7.2K RPM. This total bytes written is a little bit unhandy criteria. So the industry introduced this disk or device writes per day. And this is what was said earlier, how often the entire capacity can be written per day over lifetime in average until we reach this 3 months retention point. Yeah, it is an average. Yeah, you can write twice as fast, then it lasts only for 2.5 years. And there are formulas how to calculate from one to the other. I mean, if there is a resource that is consumed, like the ink of the printer or the gas of a tank, we would like to have a meter, how to check how much resources we have consumed already. And here's an example how this is done in Toshiba in the SATA SSDs. So on the smart page, there is a erase counter. This erase counter goes from 200 down to 100, down to 0. At 100, it reaches this 3 months retention point. Yeah, then you can still continue, but we recommend to replace it because we cannot commit that after a power cycle all your data is still there. Actually, at 0, we don't allow writing at all anymore. This smart data or this counter in the smart is not yet standardized. So some guys don't have it. Some guys have it, but do not give the details which value it is and how it should be interpreted, what should be done. And so also guys like controller makers and software and system companies cannot rely on extracting this data as a kind of health check. So there's still a way for the industry to standardize on that. For the smart, like power on hours and temperature and all the things that you can read from the smart pages of a disk, it also take I think 2 decades for the disk manufacturer to standardize on what we are. So for the SSDs, there's still a way to go. But I mean, with a counter like this, you can not only see where you are with your endurance. Yeah, you can also predict, will I get to my 5 years or 3 years period if I continue writing like that? It's like if you want to drive from Paris to Munich, And if at the German border your tank is already three-thirds empty, you probably won't get to Munich, to your 3 or 5 year point. And then you can trigger an alarm and go to the gas station and replace the SSD. So what we have today as endurance classes in SSDs is this 0.1 to 0.3 disk writes per day, which is used for laptops and for boot applications, usually for a 3 years warranty. And here we have this 7 or 7.4% over provisioning. So if there's 1024 gigabyte of flash installed and 1024 gigabyte capacity provided to the user, 7.4% over provisioning. Don't do too heavy writing, so don't rely on the megabyte per second of write performance because of this low over provisioning. On the other hand, in a gigabyte with 0.3 disk writes per day, you can write 300 gig a day. Yeah, you can use them as a boot, or people are even using them for more like content delivery applications where the content is updated not too often because they enjoy the low price. This stands for currently about around 50 cents. Then we have this 1.3 disk writes per day. They are usually coming in SATA, but we in Toshiba, we also using the kind of economic multi-level cell technology also for SAS because of people like the dual channel SAS 12 gig for kind of more professional applications. 1 to 3 disk writes, 1 to 3 overwrites per day. We call it read intensive content delivery streaming. But even in virtualized environments with a little bit care of sequential data, not too many random writes. So for VMware, for example, 3 disk writes per day on volume data is enough nowadays. They wanted to have 10 initially, but now they are okay with 3 disk writes per day. And it seems that this 3 disk writes per day for many kind of volume data applications, even in virtualized environments, is enough. And they are not too expensive, in the range of $1 per gig. With a gigabyte of flash installed, there are models which provide 960 gigabyte user capacity with 1 disk writes per day at 12% over provisioning, and at the same physical model with just 800 gig give 3 disk writes per day, meaning the 37% over provisioning. So you can also see from these numbers that kind of that one will have a more stable write performance because it has more room for kind of pre-erasing. Well, this is just an example. In the lineups of the vendors, there are the 500 gig and 2 terabyte models, 4 terabyte, with the same ratio. 10 disk writes per day is mainly on SAS because 10 disk writes per day is a lot. That is 10 disk writes per day. On a 1 tera SSD means 10 terabytes a day created, shuffled, read and written. It's done in servers and databases. There are no client applications. So here on a 1 terabyte, we are using this selected enterprise MLC with 800 gigabyte of capacity. Same over provisioning here, just kind of higher quality flash. You can overwrite 10 times a day, but at cost because of this enterprise stuff. And then the very high end with 30 disk writes per day. For larger capacities, that's virtually unlimited. There are no servers generating so much of data. For the smaller capacities, you use as caches, logging, accelerations. Here, the concept is simple. Kind of, it's the same hardware like that, just going from 800 gig to 400 gig by much more over provisioning or this pseudo SLC operation. Just half the capacity means just double the price per single gigabyte. Well, we all know why we use the SSDs. So the hard disk are, even the fastest hard disk, kind of in a simple volume mode are around 300 IOPS. SSDs 50, 100,000 IOPS. We heard 700,000 IOPS for the PCI Express interface. The sequential data rate is not so drastically improved because of the spinning disks. They are okay for sequential mode if they don't seek, but still like up to a gigabyte per second in an SSD for read. So to summarize, we are using SSD because they are fast. We need to understand that HDD and SSD are different. Kind of a one-to-one exchange is not possible. The SSD application is sensitive to workload and for the write workload because we are consuming our amount of writable data into an SSD and then it just stops. Well, the client SSDs, due to the low over-provisioning, don't really work in RAID or cache applications. They're okay for read intensive, they're okay for data center, they're okay for enterprise application, but the writing workload must be controlled, must be known, and should be monitored by checking the erase counter. And on a system level, kind of if people do use kind of the low endurance SSDs, there should be also a kind of wear leveling on system level. If you build large volumes with that, you should control it in a way that kind of the write workload is distributed equally over all your SSDs. The disk writes per day is the key criteria for the selection and for the quality. It depends on the flash quality, the screening for the enterprise level. And my boss told me I should do at least a little bit of advertisement for my company. So I would buy SSDs only from flash manufacturer who have control over this raw components. Well, one other thing, if we are at comparison of SSDs and HDDs, the HDD usually fails by the spindle motor failure, which is unpredictable. It can happen any second. The SSD fails by reaching the maximum write endurance. This is very predictable. We have a counter. The SSD tells you in advance when it will fail with this mode. Well, there are also kind of the normal technical failure, this MTTF or MTBF of SSDs, but as there are no moving components, they are all 2 million hours or 2.5 million hours for the SSD. And that's it. A final word, if we put all the storage component technologies in a comparison, sequentially from tape to hard disk to SSD, it is slightly improved. Yeah. The major improvement goes for the IOPS. For the tape, there are no real number for IOPS. For the hard disk, with 150. On the other hand, kind of the cost level per gig also tell us that kind of tape will be used forever, and probably also hard disk will be used forever for the data that need some access from time to time, so cannot go into the tapes, but is not kind of the active data that need the high IOPS. And at the moment, there is this ratio between SSD and hard disk in cost per gig, but well, we are seeing SSDs approaching the 20 cent, 15 cent, maybe 10 cent per gig, but at the same time, we are seeing that with shingled magnetic recording and bit pattern media and all these hard disk developments, they will be at 1 cent per gig here when there are 10 cent per gig there. So they will coexist probably until I retire. Okay, that concludes my presentation. Any questions, please? Okay, so the power loss protection, well, it's not about the flash technology. This is why it's not here. But just to mention it, in a hard disk, when a hard disk receives an unplanned power loss, so it cannot be parked in a controlled way, then we have enough energy in the spindle. So we switch the motor to a generator, and we have enough energy in the rotating spindle to write all the caches on the media, pull back the arm, and park it on the ramp. So IT industry, every one of us is used to the fact that there is energy in this hard disk, and it can accept power loss, and all data that kind of the controller has confirmed to the host as data is there will be always on the media. In SSD, there is no energy. There's no rotating spindle. So in case there's an uncertain power loss, data which is in the caches will be lost. Since we are used to the HDD behavior, that is not acceptable. So there are no countermeasures in the system. You could do countermeasures in the system against that. But as we are used to HDDs, there are no countermeasures. In order to make them look the same, what industry has implemented is supercaps, batteries or something in the SSD that saves the data that is in the caches into the flash cells, close to flash cells in a controlled way, even an unexpected power loss. So if you select SSDs, make sure that for if you are used to HDDs, if you are used to unexpected, if you have to cope with unexpected power loss, you need this PLP power loss protection. In a laptop, that's not an issue because there's a battery, and if the battery goes down, it makes a controlled power sequence. There's no issue there.
Any other questions?
So you mentioned the standardization of the when am I going to run out of gas? This is definitely like a big problem for software and systems people. What do you see as the future for standardization on that front? Is it just like it'll happen in 20 years or?
Well, this is inherent in the technology. We cannot do anything against this. If we would do more over provisioning, then it will have a higher cost. And on the other hand,
just standardizing on making that information available to the operating system and the software.
The smart data.
Okay.
The smart data. So that we can instead of us software guys having to detect every different manufacturer, every different drive, and then consolidate it into one number for the user, like be able to just query the drive. What percent are you left, and then pass it up to the user.
The issue here is we are trying to standardize it, and the larger manufacturers, they have joined, they have built associations and are discussing, but still there are, I would say, too many SSD manufacturers. There are still about 40 to 50, and it seems to be impossible to get them all on the same table to agree here. But there's a consolidation process. At the same time, if the big manufacturers talk to the value chain players, so I'm in discussion with Avago, Adaptec, our guys in Japan are in discussion with all these guys to, at least use the things that is in our data sheet that we provide to turn it into valuable information for the upstream users. It will take a while. It also took a while to make everyone understand that this is important information. That this information must be provided. So we are almost there yet. That most of the people understand. That most of the people see the need of providing this information and using this information, calculating on this information. So I guess it will be happening as we sit here.
Where do you see the size of pages going on flash technology as well as like the race blocks? And is that information that's going to be accessible to software developers, and to be able to inquire the devices to actually make smarter decisions?
Well, it's in our data sheet. We publish this information. At the moment, SSDs are between 256 and 512. With new generations of 3D structures, it will probably go up to 2024, 2048. But then it also depends on the decisions of the flash designer and the trade-offs of the raw flash designer, and these guys are far away from us. So we don't really know, and kind of it's deep down physics. So we don't really know where the direction there goes.
you were planning to elaborate on the on the trim issue. You said, well, trim doesn't really solve the effective erasure of the pages.
Well,
leave it to the controller. It can handle it more smartly.
If trim from the operating system works, it is an ideal situation for the SSD, because kind of this trim triggers a very efficient garbage collection process into an SSD. So if the host does not tell the SSD which data is not used anymore, the garbage collection can only work on the over-provisioning area, where it's obvious that the data in the over-provisioning, so which is beyond the capacity of the SSD, this data is obviously not used anymore, so it can be erased. If the trim command gives relevant information, gives exact information of data in the user area not used, then the garbage collection can work on that as well. It's just that what I am seeing is that kind of it works in modern operating systems on laptops somehow, but in server and in RAIDs there is no support for passing trim information from a host through RAID controller expanders onto the single enterprise device. And this is why the infrastructure for passing this information from the host into devices in enterprise environments is just not there.
If I can jump in there, so suppose I have modified ZFS to reliably issue trims for deletes. And I have tested it with some manufacturers and some models of SSDs, SAS SSDs, like enterprise class, and they really, really hate it. I mean, like, the SSD will basically go down to 1% write performance while I'm trimming. What is your take on that? Do Toshiba SSDs not go belly up when I start trimming up several gigabytes worth of space?
I don't know. We haven't tested that. Yeah, but
Okay.
there is.
Give me a call.
Yeah, the problem here is the programs in the SSD controller are pretty complex. So much more complex than this kind of just data passing in HDD. And if you have complex programs, complex tasks running in several entities, there are often conflicts if some workload comes. If something comes that was not expected by the controller software designer, that we see such things really happen.
Okay, so basically you're saying that not only do operating systems in the enterprise space not support trim, but they shouldn't even try.
No, it sometimes causes conflicts. So if you want to use it, then kind of try it with your specific SSD from the supplier that you want to use and see whether it works. I cannot.
So it's hit and miss.
Yep. Trial and error.
Cool, fantastic. Any more questions?
Yeah, just kind of one final word to that. This is why we are giving samples to companies, not only end users which are buy from us, but also software makers, controller makers, giving samples and supporting the evaluation. It's important for SSDs. So many strange things can happen in SSDs that this is an important task. We are aware of that, and we cannot fix everything because it is not just a single host like in a laptop working with our storage component. That as it is a trial and error process, we are aware and we are open to support everyone who want to evaluate.
Yes, the diskful write per day is for random write.
Yes, this all the numbers here are for random writes of 4 kilobyte blocks.
There are a number with sequential write.
Yeah, we also have numbers with sequential writes, and for our SSD it depends on the type. So for this 4 kilobyte blocks, there is a certain write amplification which you don't have if you just sequentially write. And as a rule of thumb, for a 64-128 sequential write, the disk writes per day is between 2x to 3.5x of the random numbers.
It depends on the technology.
Yeah,
MLC, TLC.
It depends on the underlying flash technology, so there's no common answer to that. Again, it is strongly advised to do a test and monitor your erase counter with the specific workload in your systems. Yeah? Then you can have the numbers in your system.
On the smart control is aware of that usage of the SSD.
No.
Of the cell.
No, it's just that let's say if you have a very sequential workload, kind of gigabytes of sequentials, and you want to know the disk writes per day under this particular condition, because the disk writes per day in the datasheet is 4 kilobyte random blocks. You run this for a week or so. You know the amount of terabytes or petabytes you have written in, and you can see where your erase counter is. Then you can calculate back. Or give me an email, I can calculate it for you.
One more thing about page sizes. You showed there the typical page size is 4K. I have seen SSDs in the wild that are 8K today, and presumably 16 or 32K is going to be coming down the line. When do you see that happening from Toshiba? If at all, or within reasonable time? So that we can prepare inside of ZFS, because that's going to mix things up.
So with the 50 nanometer technology, as far as I know, we go to 8K. But it's not determined yet.
Anyone else? Well, thank you very much. That was amazing. So thank you very much for that, Rainer. That was a terrifying insight into NAND technology. So maybe you might reconsider people who want to be doing all flash arrays or all flash pools. Hybrid is the way forward. I think that's what I heard.